Let's start off with, let's see, we got everybody here. Okay, where did we leave off on going over answers? 3, 4, 5? 5. Did we do 5? Yeah. All right, so let's look at those. So we did this one 1/30th? Okay. All right, so gateway test tomorrow. Nothing new to add. I think everybody was here yesterday, and we talked about these things. So today's about asking some final questions and reviewing, a few more practice ones like we did yesterday, kind of together, and then you'll be ready to go. Because that's your last chance where this is all we focus on, right? Just like what we did before. So we take the gateway test tomorrow. We'll probably pass back some of, if not all of whatever those packets that you turned in earlier, and then we will, start doing some of those as you've seen already, and maybe we'll do a few more today. There are quite a few just with this little bit of chapter 5 that we've done. There's quite a few multiple choice questions in the packets we can do. For example, just with what we've done now in chapter 5, I think in one of the packets, I think we do all the rest of the multiple choice, but like 3 of them. You know what I mean? I mean, just with a fairly small amount, just doing anti-derivatives, integrals, those kind of things. Free response, we still have some things to do, and we still have some other applications and things, obviously, to use this with. But anyway, so we'll start working in that a little bit, then we'll just continue finishing up chapter 5, starting on Friday, and getting into that. So if you don't pass it, you've got to find that time to get it made up. Okay. Preferably for the gateway test before school. It was one thing after school to come in to the gym. It's not the greatest place to take a quiz, but at least you can do it. Well, now I'm going to be coaching track. That's even harder. So now if you want to do it after school, you'll have to do it on the run while we're out running on the road. That's not a lot of fun. Actually, just kidding, because I don't go out on the road run either. But, it's not going to be, I mean, it's just going to be better if we come in the morning for the gateway test, especially those don't take as long. Come in the morning before school to get those done. Or if you have a 4th block free, then you can do that too on those things. But, anytime we have a quiz or something to make up, I mean, we'll figure it out. But morning is going to definitely work by far better. Here in the spring. But anyway, you've got, it's the same deal as last time. So you pass it on the first time, 30 out of 30. Then you get a couple more attempts to get a 27 out of 30. All right. And then a couple more attempts after that. They have to be timely. You can't wait for a week and a half and then try your second attempt, right? If it's a week and a half later, 27 out of 30 is not a chance anymore. Now you're down to 24 out of 30. Right? I mean, you've got to come in within a day or two to at least make another attempt, and then the next day or two you make another attempt, or at least be talking with me about your plan for getting those made up. Okay. All right. So here, that was number 5. All right. So here we go with number 6 is an integration by parts. This is pretty much what the integration by parts look like. We have kind of a mixture of different function families. But not only that, the fact that there is no inside, there is no u that we could pick, and the du would be setting there with it. There just isn't anything like that here. And so it's a last resort is this integration by parts. Remember, at most, a couple of those, or 3 maybe at the most, the vast majority are going to be u substitution or just regular antiderivatives. So anyway, if you decide that it is an integration by parts, then Leate would say the log would be the u. So you do the Leate, log would be the u, this would be the dv, so the du is 1 over x, the v, the antiderivative is that. So when you go to put it in here, you got u times v, which is that, make sure you put parentheses around that or that's wrong. Minus v du. So when you look at this, you say, okay, v times du. Well, I'm going to need to multiply that and simplify it. So I don't think you should write it down right away. I usually go off to the side here and say, okay, I'm going to take 1 over x times this. That 1 over x is going to cancel an x here and cancel an x here. Okay? And so it ends up being this. Now I can do my antiderivative. Raise it up to a 6, divide by 6, I get 1/18. Antiderivative of 8 is 8x. Don't forget about distributing that negative sign, right? All of those things can be little things to make it go wrong. Okay? So be careful there. All right? And again, we'll have some work time here later. And if you want me to go back and look at some of these screens, we can do that. All right? Number 7. Number 7 is just a straightforward antiderivative. I mean, there'd be no reason to let u be anything here. I mean, it just doesn't work. You're just going to distribute that x to the 1/2 through there. And then you add the power. So 1/2 plus 3 is 3.5 or 7/2. 1/2 plus 1 is 1.5 or 3/2. And now you just do a straight power rule on those. Raise it up 1 to be 9/2. 2 9ths, that'd be 5/2, 2/5. Here you got to kick out a 1/4 because of that 4 right there. So you get 5/4. Okay, so that's number 7. Number 8. Again, this is one of those that can throw people off because you're looking. Maybe you've done, and the gateway test is like this too. They're all mixed around, and all of a sudden you might have an easy one or a couple hard ones at the beginning, and then all of a sudden an easy one. And I've had several people ask me on this one about a u substitution or something. The most common thing somebody did was they tried to let u be the top. Well, then the du would be 20x to the third, and then it's like there's no x to the third setting there anymore, so we wouldn't do that. Now, the first problem we did, I think, had a square root of x on top. Well, that's x to the 1/2, and then it had a square root of x on the bottom. Well, if you let x to the 1/2 on top, and the derivative is 1/2 x to the negative 1/2. Negative 1/2 is a square root on the bottom, and it was sitting there. That's good. Now, if you had an ln on top, that would be good. If an ln was on top, and then you did the derivative of that, that'd be 1 over x dx, and that's what you have there. You have a 1 over x dx setting. But it's not there. I mean, there just is no u substitution. It's simple. It's just split it up. Split it up. Right? But sometimes we don't see the simple. Sometimes we're trying to make it too different. So we just split this up. 5x to the third plus 1 over x. So it's a straight power rule. It's a natural log. And then we put our e and our 1 in. And don't forget parentheses and all that. And then simplifying it, we should take 1, take away 5/4 would be negative 1/4 and so forth. E to the 4th, just leave it. Right? It's all no calculator. Okay, that's number 8. Number 9. Now this was one in the homework, I think, wasn't it? Wasn't this one in the book, in the chapter 8? No, I was thinking it was, but maybe it wasn't. Anyway, and there's not an A and a B, right? I don't know if those in the class, but there's nothing there. But this one turns out to be an integration by parts. This one's a little trickier because, again, like I was just saying, if that would have been an x on the bottom, then this would have been a u substitution. If it wasn't an x squared, if it was just an x on the bottom, we would have let u be the ln x, and the du would have been 1 over x dx, which is sitting right there, and it would have been just a simple u substitution. Okay, but it's not an x, it's an x squared. And so you say, well, there's an extra x, right? You got 1 over x dx, there's an extra x. Yeah, but this isn't one of those where we can easily just solve this for x. I mean, we could, it'd be e to the u, but that would be weird. And you'd put it in there, and that wouldn't be anything that would be easy to work with. So that it's just not that. So you can't do u substitution. You can't split apart, just simplify. You can't. So last resort, you got to do it as an integration by parts. And so what we do is we just bring the x up here as negative 2 power. So we have ln x and a negative 2 power. So we have a log and an exponential. So let u be your log. Let dv be the exponential. Okay. The du is 1 over x. The v would be raise that up to negative 1 divided by negative 1. And now you got to take uv. So this times this is that. And then minus v du. Well, you got to multiply those two. Well, that's a negative 1x. This is a negative 1 powered. And so you add the powers. You add the power. So x to the negative 1, x to the negative 1 be x to the negative 2 with a negative on it, which turns out minus to a plus. And now you can just do that antiderivative. Raise it up to negative 1, divide by negative 1. Okay? So that was pretty tricky one. That doesn't look like the other integration by parts ones. Now, if I would have written it this way, you know, how I write the problem could sometimes make them a little harder or a little easier also. And I take that into account when I talk about, okay, there's going to be some that are a little easier, some that are kind of medium, some that are kind of hard, right? If I write it in a way that makes it a little easier, then, you know, that counts as one of the easier problems, right? So if I wrote this problem this way, to me, that's easier. That is easier to identify that this is an integration by parts. Written this way, you know, then all of a sudden that probably throws you off a little bit. Okay? All right. So look at 10. 10 is an arctangent. Now I want to talk about that as soon as we get done checking the last one here. I want to talk about the arctangents and arcsines a little bit. But this is a 1 plus u squared, right? That's an arctangent. Now you have to think of the 4x squared. You have to think of that as this, right? So what you have is an arctan 2x. So you're going to have to kick out a 1/2. So you got the 3 on top, you kick out a 1/2, that's why you get this. Now you could go through and actually do it as a u substitution. You could say, okay, let u be the 2x. du would be 2dx, so you divide it over. So that would give you a 3/2, a 3 would come out, the 1/2, the du, and then your u is your 2x, so you'd have 1 plus u squared, so that's an arctangent. Okay, so you have 3/2 arctangent u, and then you put your 2x back in. Okay, so you could go through the u substitution, or you could just notice that it's that pattern. So I'm going to talk about those arctangent, arcsine ones a little bit more today here. But any time you see a, you know, 1 plus something squared, you know, you're thinking arctangent. Or you see a square root and a 1 minus something squared, you're thinking arcsine. Now, it might not always be that. What if this problem would have been this? What if I just stuck 3x up there instead? Now it's a straight u substitution. Now the bottom is your u, the whole bottom, and then the du would be 8x dx, and that x dx would take care of that x dx up top. The 3 you just pull out, the 8 would be a 1/8, but you could deal with that. But that would just be a straight u substitution, not an arctangent. Here's one that nobody's asked about it, and I don't know if you've run into it. Most years, somebody will ask about this one from the book. But there's one in the book that looks like something like this. Okay, there's one that looks like this in the book. And people struggle with it because you say, well, I see this x up here, so I could let u be the 1 plus x squared. And then the du is 2x dx. The problem is we don't have an x dx up here. We have a 3x plus 4 dx, right? We don't care about that 2. We can divide it over. Don't really care about the 3. But we have that plus 4. Well, that really changes things. Okay? Well, it turns out what you have to do to this one is split it up. They say, well, wait a minute. I thought you couldn't split a denominator. Well, you can't. So here's how you would split it up. You would split it up like that. You can't split the denominator, but you can treat it, as long as you keep the denominator together, you can do this, right? Doesn't this make sense? Isn't that okay? Right? You can add these back together. They have common denominators, so we can put that back together. So what are you going to do for this part? U substitution. What are you going to do for this part? For our tangent. For our tangent. You see what I mean? So you get one like that, sometimes that's the way to do it. So anyway, you see the 1 plus x squared, okay? And what's that? And then you add them together, yeah. So you'd have whatever plus whatever for our tangent, yeah, for our tangent plus c, right? That is, I think, if I can, I bet I can just see it here. Number 41. Number 41 in the book on page 341 would be that case right there, and that's one I've often had people ask me about. But I just thought of it when we were talking about arctangents. No one's asked me about that one, so maybe no one has tried that one yet. But see, that's the kind of thing. That's where we talk about a lot of practice. There's so many of these little things that these little things you run into. We've talked about splitting apart fractions. We've talked about arctangent. We've talked about all of them. We just haven't seen it quite that way in a problem, right? So the more of them you do and the more of them you ask me about, if you don't know what's going on, the more prepared you'll be ready to go. Okay, so anyway, that was that one. I'll talk a little more about arctangent in a minute. And then this one is just a basic, but this one is just a basic U substitution. So it's all kind of nice after running into a few of those kind of more unusual ones. You got, inside 2x cubed, the du will be 6x squared. That's nice because I got an x squared setting there, which is what I want. And so this is just really a pretty straightforward U substitution. So, but again, the more you've practiced them, the more you've done them, you start noticing those. You think back a week, and all of a sudden we were this whole idea of U substitution, I think, was pretty strange. But now, hopefully, I think it is true for some of you, for sure, that I've been talking about, is that now you see something like that, and you just see it, can't you? Right away, you can say, okay, let that be U, du, here we go. Okay?
We forget the plus C is or
Let's put it this way. I'll probably remind you at the beginning, hey, don't forget to put plus C on them. Maybe halfway through I might say, hey, don't forget, you know what I mean? I don't want to give you permission to leave off the plus C. I think it's important. So we need to understand that. However, if it's not there, I'm probably not kind of wrong. But, it shouldn't be not there on all the problems, right? But, you forget it once in a while again. Now, here's what you can't do. Here's what I don't want you to do, is just mindlessly putting a plus C on everything. Because I've had people actually do this. They get this problem, and then they go 130 plus C. That would be bad, right? Because that shows you have no concept of what's going on and why there's a plus C, right? You're doing a plus C because a general antiderivative like this is a function, and there's no initial condition, so every function has an infinite number of antiderivatives, and they're all vertical shifts of one another. That's what the plus C represents. When you do a definite integral is a fixed piece of area, a number. The plus C doesn't make any sense on the definite integral, so there shouldn't be a plus C on those. Okay? On the gateway test, out of the 10, there's probably a couple that are definite integrals where you get a number answer. The rest are just general antiderivative. All right, finally, did we do number 11? That was the one we just did, number 11. Okay, so let's talk about arcsine and arctangent here a little bit. Matter of fact, why don't you turn to page 333 in your books. Let's do that here first. Okay. So page 333 in your book has that list of antiderivatives we should know. And remember, the whole goal of our three techniques. Okay, so technique number 1 is really not a technique, but just doing a basic antiderivative. Now, that might mean you have to do some algebra. You might have to do a little rewriting, like of this one, number 8. We had to split it apart first. This integral doesn't look anything like page 333. However, when we split it apart and do this, we have a power rule and we have an ln. And now it does. So any of our three techniques, the whole goal is to rewrite it, maybe with some algebra. Okay, go back to this one. Here we just had to distribute. And then it looked like 3 power rules. Well, no, an exponential and a couple of power rules. So maybe we have just some algebra or some rewriting that gives us an integral that looks like page 333. Maybe we do a integration by parts where this integral that we're left with, we can just do page 333. Or we do a U substitution where the integral looks like page 333. And that's the whole point, right, of all of our techniques. Okay, so going down through there, we have the power rule, we have the ln, we have the e to the x. The fourth one down, don't worry about. 2 to the x, we know the derivative is 2 to the x times ln2. The antiderivative would be 2 to the x times 1 over ln2. But I'm not going to give you any of those. Now, maybe on the website problems that I showed you, it might show up, but don't worry about it. It's not going to get it anyway. So we can ignore that. Sine, cosine, secant squared, the antiderivative is tangent. We should know that. not tangent squared, just tangent, okay? Cosecant squared, it's negative cotangent. I'm not going to put that on there, but maybe in the, again on the website, it may show up. And then the last two, the arcsine, the arctangent. Why isn't there an arc cosine on there? What was the difference between arcsine, arc cosine? You remember on the derivative rules? The derivative of arcsine was 1 over the square root of 1 minus u squared. No, what was arc cosine? It just had a negative 1 on top. It just had a negative 1 on top. Well, if we had that at an integral, we just pull out the negative, and now we turn it into a positive, and then it's arcsine. So the only difference there would be that negative, okay? So we don't really need an arc cosine, all right? So, and remember, arcsine has a square root, and it's minus, and arctangent has a no square root, and it's plus. Now, so let's talk about that. So we already talked about this scenario. So if I had 1 plus 4x squared, or I had 1 over the square root of 1 minus 9x squared, okay, then we would want to be thinking about that as 2x quantity squared. And so this would be an arctan of 2x, with a 1/2 kicked out. And this would be an arcsine of 3x, with a 1/3 kicked out, because we can think of that as 3x quantity squared. So it's a 1 minus u squared situation. So a 1 plus u squared or 1 minus u squared, the u would be 3x root 2. Okay, so we want to be able to recognize those. Okay, now, also, if you had this, okay, that's also an arctangent. Now, the rule for arctangent, there has to be a 1 here, right? It has to be 1 plus x squared. Same thing with arcsine, it has to be 1 minus x squared. How can we get a 1 here? No, we don't multiply, because then that changes it. We factor out a 4. Now you might say, well, you can't factor out a 4 here. Well, yes, you can. Anytime you can factor out anything. We just don't do it in algebra class because we're doing it with integers. We always want it to be integers. We don't want to get fractions. When you factor out a 4, you're just dividing by 4. So what you would get here is you would turn this into 1 plus what? 1/4 x squared, right? You would turn it into that, okay? Because that would distribute back. 4 times 1 is 4. 4 times 1/4 is 1. So that would work. And so now what you've done, and then what can we do with this 4? We could pull it out as a 1/4. And so now look at our bottom. Our bottom would be actually what squared? 1/2 x, right? This 1/4 x squared would actually be a 1/2 x quantity squared. And so this would end up being a 1/4, an arctan of 1/2 x. And then what would we have to kick out because of the 1/2? What do we kick out if it's a 2x in there? We kick out a 1/2, right? So if you have a 1/2 x, we're going to kick out a 2, right? And so this ends up being 1/2 arctan 1/2 x. Okay, is what we would end up getting with that right there. Now I'm not saying it's going to be on there. That would be a harder one, obviously. But just to point out, yes, you're on the lookout for a 1 plus x squared or a 1 minus x squared with a square root for arcsine, arctangent. If you had something other than a 1, you could get it to be a 1 no matter what was there, okay? And then you could pull that out, and then you would have the look you wanted for an arctangent, okay? All right, so that's just something to be aware of those. All right, what do you have? Anybody have some that they've tried in the book here or in the packets, and you had questions about? Yes, sir. What is that?
Integral of x cubed minus the square root of x squared plus 2.
Times x squared plus 2? Like that? Okay. So now again, because of how many of these I've done over a long time period, so this is going to have an extra x is what's going to happen. You're going to want what would be the probably the obvious choice of what to let ub. The inside, the x squared plus 2. Now, it is possible, this might be one, was this in the book or the LH bag? Okay, it might be that this one is like the one Cody asked about the other day, where you had a couple different ways of doing it. Remember, the book had a square root on it when it picked the u, and sometimes it didn't. I would suggest letting u be the x squared plus 2. Okay? I think that would probably be the way to go on this one. The du would be 2x dx. And then we could move that over. And we get that. Now, our substitution would look like what? Well, this would be u to the 1/2. Now, the x cubed is going to have to get split into x squared and x, looks like. Okay? Because what do I have here? I got an x and a dx right here. So that's going to be a 1/2 and a du right here. And then I've got everything taken care of except this x squared. Well, what's x squared? U minus 2. So x squared is u minus 2. So I can take out that x squared and I can replace it with a u minus 2. Okay? And so now what happened was, see, and here's the problem. This x cubed, I can't distribute it in there. I can't do any algebra to this. But now I can. Now I can't because I don't have a power on that u minus 2. So now I can just leave the 1/2 hang out here. I got u to the 3/2 minus 2u to the 1/2. Again, I can still leave the 1/2 hanging out here. Or maybe should bring it along as I do each one. So raise it up to 5/2, that'd be 2/5. So that'd be 1/2 times 2/5 u to the 5/2. Raise it up to 3/2, divide by 3/2, so that'd be a 2, that'd be a 1/2, and that'd be a 2/3. U to the 3/2 plus c. Let's go through that again. So I raise that up to 3/2, divide by 3/2, so that'd be a 2/3. The 1/2 has to come along, and the 2. Now you can see the 2 and 1/2 are going to cancel, so that's nice. Okay? And then these 2's are going to cancel, so it's going to be 1/5. Put my x's back in now. 2 and the 1/2 are going to cancel, so it's going to be 2/3. Right, so it's going to look like that. Okay, so I'm not sure that one would have worked very good if I'd have let u be the whole square root thing. Here, let's do that in black. If I'd have let u equal, here's what you would have possibly done. I don't know if you want to write this down yet, but if you let u be, this is what happened the other day on that one that we talked about, where this is what the book did. If you let u be this, you normally don't want to do the du of that because it can be really messy. But what you can do is you can square both sides, and you could get this. And now you could do the derivative of both sides. So you'd get 2u du, and you would get 2x dx. Does that make sense? You see what I just did there? Okay, now the 2's would cancel. So now look what your integral, let's see here. So this could be what? What would this be? That would be u. The x dx would be what? The x dx would be u, so that would make this u squared du. You see what I mean there? And then what am I left? What's left? The x squared? And what's x squared? U squared minus 2. So this becomes u squared minus 2. Whoops. And do you see how now I can make that u to the fourth minus 2u squared? And so now I can do my antiderivative, so that'd be 1/5 u to the fifth minus, and raise that up to 3, divide by 3, 2/3 u to the third plus c. See where I'm going with this? And now my u is this, which is x squared plus 2 to the 1/2, right? So now I probably would, if it were me doing it, I just would put my square root in, my u. So I'd probably go u equals square root x squared, come on. Even my marker didn't like this problem. It's crazy. Minus 2/3, and then square root x squared plus 2 to the third plus c. Now let's compare that answer to this answer. Aren't those the same? They are, because what this is x squared plus 2 to the 1/2, so you'd have 1/2 to the fifth. What do you do power on power? Multiply. So you'd have a 1/2 times 5, well guess what, that's 5 halves. Here you'd have a 1/2 times 3, that's 3 halves. So see how it'd be the same? So that's a little bit like the one that was in the book. Now I don't usually recommend that. I don't let u be the whole square root thing, because if you do that, you don't want to do the du. Probably want to square both sides, like I did, and then do your du, or your derivative thing, and then that sometimes can work okay. So I'm not sure what the back of the book would have said on that one, but I typically tend to go with that, let u be the inside. That just seems to be more comfortable for us. But that's a good one. That's a good one, because that shows a couple different options for the u. Okay, all right. What else? What else? What else? Anything else?
59.
Yeah, what do you got?
Integral of x tangent of x squared.
X tangent of
X squared.
x squared. Oh, yeah, okay, I can see where this is going to get tricky here. Because you're going to, well, what's your start going to be, Kate? What do you think?
I didn't even know.
Well, I mean, there's not many options, really, right? I mean, first of all, let's go with the assumption we can't do just a basic thing. And so the next thing would be u substitution, right? And where do you usually look for u? Inside. So you'd let u equal x squared. Yeah, I think that's exactly where you would start. Now, again, you can't, I mean, yes, if I'm going to get in my car and go on a trip, I'm probably going to get a map, and I'm going to look, and I'm going to look at all the routes, and I'm going to plan the whole thing out before I start. You can't look at that here. You can't not start this because you don't know where it'll end up, right? You want to look maybe a couple steps down the road if you can, but you can't not start just because you can't see the whole thing. You know what I mean? So start. Say, okay, I don't know where this is going to end up, but the thing seems to be to let u equal x squared. Now, the other reason, if you just want to look at a couple steps, what's the du? It's 2x dx, and that's sitting there, right? So both of those things would lead me to think I can just do this. Now, my first comment when you gave me this problem was, I said, oh, yeah, I can see where this is going to be a problem. Well, I've traveled this road a lot, right? So I already know I can see 4 or 5 steps down the road, but I've done way, way too many of these, right? All right, so so I can see this all gonna happen here, and now what do we got? Well, you're going to have tangent of u, right? That's going to take care of that. The x dx is going to be 1/2 du. Well, now we get to that. Well, how do we do that? No. We actually did this one already, I think. We've changed it to sine over cosine. Now, here's your option. You can either remember that this answer is going to be this, which it doesn't seem like maybe we did. Okay, so that's okay. Did we do this one? That was the other class. Okay, that might have been the other class. So maybe if you were gone, you might have watched the video. You might have saw the video. But yeah, the answer is going to be this. So you have an option. You can either memorize that the antiderivative of tangent, because that's not on page 333, is it? You can either memorize that it's this, or you can say, okay, if I get a tangent one, what I'm going to do is I'm going to make it sine over cosine. And then I'm going to pick, well, I can't use u because I'm already using u, so let's use w. I'm going to let w equal, what's our other option? to pick u. The inside, what's another one we've used? The bottom. We're going to let u be the bottom. Because what, or w in this case, because what's the dw? Negative, because we're doing the derivative now, right? So it'll be negative sine u du, which is setting right there.
Oh, yeah.
Because we're doing the derivative, right? We're doing the derivative. Okay? So, what does my integral become? My integral becomes a negative, so the sine u du comes out as a dw, and the bottom is cosine, which is my w, so I have 1 over w, and what is 1 over w, antiderivative? ln. So we get negative 1/2 ln w plus c. Now what was w? W was cosine of u. What was u? X squared. So we end up with a negative 1/2 ln cosine of x squared plus c. Okay? So again, if we memorize that antiderivative of tangent is negative ln cosine, then we'd have had our 1/2. So we'd have had negative 1/2 ln cosine u, and of course we had the x squared, so we could have had. So you can memorize it. We can make the list on 333 bigger. There's nothing magical about that. We just stopped there. The book just said these are the ones we should memorize. It didn't have cosecant squared on there. We probably should know that one. And maybe we should know tangent. I don't know. You know, another one we haven't memorized is ln x. What's the antiderivative of that? Well, we did it with integration by parts here today. I think it was x ln x, or maybe we did minus x or something. I don't know. Something like that. What?
Oh,
Question?
so it is x squared and the cosine at the bottom?
No, well, okay. What on the bottom, what I was doing was I was telling you that the antiderivative of tangent x is this. Yeah, we were doing tangent u, so it'd be negative ln cosine u, and then the u would be x. Yes.
Did you do that by integration by parts?
No. No. Here, because what would you do? This is algebra, this is trig. So you'd have to do the u equals x, and the dv would have to be tangent x squared, and you can't do the antiderivative of tangent x squared.
Well,
Yeah, you just make u tangent dv.
Yeah, okay. See, well, let me answer, there's two questions, let me answer both of them. Claire, no, you can't because it's got the x squared in it. So that totally changes things, so then that's not this, right? Because that's, right, if you had a tangent 2x, yeah, you kick out a 1/2 or something, but you can't kick out anything when it's an x squared inside or something. You can't just do the antiderivative of this. Because of that x squared, it changes everything. Okay? So Cody, let's go to your question. Could you do switch around Leonte? Okay, let u be the tangent of x squared. Here's the road you'd go down if you tried this. If you tried this, let's just see what would happen. It's going to be ugly. So this derivative of tangent is secant squared, leaving this alone, right? Times the derivative inside, which would be 2x, and then dx. And then here the v would be 1/2 x squared. Okay, so now you'd have u times v, so we'd have 1/2 x squared tangent of x squared minus the integral of v du. So the 1/2 would cancel the 2, the x and the x squared would make x cubed, so you'd have x cubed secant squared x squared dx, right? The goal of integration by parts is to what? Get an integral that is simpler. What did we do? We got an integral that was harder. So that's where you know you've hit the dead end, right? So I'm not saying you might not go down that road. So then know when you've hit a dead end, right? Know when, okay, now I can identify this as a bad road to go down. So I get there and I get here and I'm like, oh my God, I don't know what I'm going to do with that, right? I mean, you can try some things, but there wouldn't be anything there that would really work. So that's when you know. I can't think of an integral where you can do it with use substitution or with integration by parts. It's one or the other. Now there might be one out there. I can't think of it though. I don't think I've ever seen it. So yeah, that one's just going to be a use substitution. All right, let's practice. Those are good questions. Let's practice a few and see how we can do here. And I've got a handful, a little bit less than yesterday. But let's see. Again, sometimes the danger on when we go over, I like to spend some time answering your questions because if you worked on some and you ran into a roadblock, you want to see why, and that's good. But then we don't want to spend too much time working just the hardest ones. Because number one, we lose confidence and we think we don't know how to do anything, maybe. But also because we want to make sure we can focus on, just the normal kind of basic ones too. And so hopefully we're getting close. Hopefully, I got 8 of them here, so hopefully we can do pretty good on this. Now, I will admit there's a couple of the definite integrals are getting a little tricky with some fractions and stuff on number 2 here and number 3. So if you get into some messy fractions, do the best you can. Try to get it without your calculator, okay? But do like yesterday, write all 3 of them down, and then we'll put up the next 3. If you just want to write down the next 3 and then go back, if you're still working on the others, that's fine. I'll give you plenty of time to work before we check on them. There's going to be 8 of them, and then if you get done with all 8, and then you just want to start working on some book ones, that's fine. And then after I think everybody's had kind of a fair chance to get through them, we can go through the answers. here's the last two. Jot those down. The answers here. Now, if you're working on one, you know, towards the end there, and you want to keep working on it, just don't look up. Just ignore me. Some of you are good at that, probably, or wish you could be better. I don't know. But yeah, you know, just keep working. That's fine. You don't want to see it yet, or you want to keep working on it. But there's what I got for one. Okay. So on the cosine, you kick out a 1/6, and so that would cancel that 6, and you got the arc sine that we talked about, and then you got, of course, the x squared is x negative 2, and just do your thing. Yeah.
Okay, so for the 4x minus 1, instead, I turn that into a 4 ln x squared. Why wouldn't that be right?
Okay. Easiest way is to check, right? When you do an antiderivative, if you do the derivative, it should check, right? So you got 4 over x squared. Now what I've said is that the only time the ln x, that rule works is when this is to the first power, right? That's the only time. But your question is, but why is that, right? Why doesn't it work? It seems like that should work. Okay, so let's do it. So what you have, you said you had 4 ln x squared. So let's do the derivative of that. The derivative of that would be 4 would hang out. The derivative of ln is 1 over the x squared, and then times the derivative of the inside, and that's why it doesn't work through the inside. The reason it only works when there's a constant on the inside, so like right here where we have cosine 6x, right, we kick out a 6, and so therefore we can undo that by doing a 1/6. The problem is when there's something like an x squared in there, you kick out a 2x. Well, unfortunately, you can't undo that by a 1 over 2x, because then you have to do a product rule or something like that. And so this just doesn't work, because now what you end up with is you end up those x's canceling, you end up with 8 over x, and that's not the same thing to start with. So it just doesn't work, right? So it turns out that unless that's a first power, can't do ln. All right, number 2. Oh, this is wrong. By the way, I forgot that I went back and fixed this and then forgot to save it. This is supposed to be minus right here, and I added. Okay, now this is probably the long way to do this one. I don't think if I had to do over again, I wouldn't do it. I'll show you what I would have done. But right here, if I subtract these, that subtracts to be 236 over 10, I think, which reduces to 118 over 5, and then that is the same as, I think, 23 3/5, or 23.6. Okay. Now, if I had it to do over again, when I got to here, I would have looked at this and said, well, that's 37.5 plus 3/5, and then that's minus. Well, this is 13.5 plus 1 is 14.5. So this would be, and then 37.5 minus 14.5 is 23 plus 3/5. So that would have been a lot easier, I think, to do 23 3/5. Probably that way instead of trying to get common denominators, especially since I don't have a calculator. Okay, but let's just go up to here first. We got to split this, right? So we got to split that, which makes 3x. And then 3 over x squared would be 3x and negative 2. So we got to split that first. Then we do our antiderivative. Now, normally we would stop and I would leave that as x to the negative 1. But since I know I'm going to have to plug some numbers in, I'd probably want to write it 3 over x. So I went ahead and wrote it 3 over x because I knew I was going to plug numbers in. If I was just doing a plus c and stopping there, I would have left it x to the negative 1. Okay, but there we have that. So now I put in my 5 and we get those numbers, put in my 3 and we get those numbers, and then you need to add it.
Would it be fine if we just kept it as like when we plugged in 5 and then the x and like substituted 5 for x?
This?
And yeah, it didn't simplify.
No. But there's not going to be much of that. There's not going to be, I mean, maybe one. Where, I mean, yes, so the answer is for definite integrals, get the simplest answer you can. Right? Now, that's a lot of pretty crazy fractions. Could there be one? Yeah, there wouldn't be more than one. I already said there's probably only going to be a couple definite integrals, so maybe one of the definite integrals gets into something like that. You know, it would have been easier for me to just done it here with mixed numbers instead of getting common denominators. But yes, you should get the simplest answer you can. Okay, and again, especially on this first one, right? If you're taking the fifth one and there's something like that on there, and that's the only thing that kept you from passing, you had this, and then you messed up the fraction. Okay, then we would talk. Okay, but yeah, that could be done. All right, number 3, 1 over 42 is what this one ends up being. You let u be that inside. The du's the 9a squared. The 9 comes over here, so you got your a squared up there. So the whole thing is a 1 over u squared, so you got u to the -2. Geez, that's 3 in a row there, Claire, that all had u to the -2 on it, right? Or u squared. Did you do ln on all of it? If you do ln on all of it, yeah, that would be good. So, but anyway, so that one's u to the -2. So you raise that up 1, divide by -1, right? And then again, I put that u down on the bottom because I knew I had to do this. Now I went ahead and got u numbers. I could have went back to x's, doesn't matter, but I went ahead and took my x numbers. Remember, these are x numbers here. Okay, so or I guess a numbers, if you will. So I'm going to take that 2 and put it right there for that a, and I get 28. Put that 0, put it right there, and I get 4. So that's where those numbers came from there. Or I could have went back to a numbers or back to a's and used the 0 and the 2. Oh, I guess I did it right down here. Yeah, I could have went back to my a's and then used my 0 and 2. I get the same thing. Okay, now how did I get that common denominator? That really, it came from this. Especially when I did this down here, I had 9 times 28. Or even on this one, I took 9 times 28. So I knew this number was made up of 9, 4, and 7, right? I mean, right here, I put my 28 in. I got 9 times 28, and I got that. Well, 9 times 28 is 9 times 4 times 7. This one's 9 times 4. So what's this one missing? I knew this was missing a 7. So I knew I could just take 7 and get the 252, right? So it was, I just went back to my 8th grade math there and my, 7th grade for you guys probably. Common denominators, factors, least common multiples, that kind of stuff. And so I got 7, so I knew this is -1 plus 7, so it was 6 over 252, which reduced it to that. But again, that's not, that's 2 in a row we did that had some kind of messy fractions. Probably not going to happen if it does not more than one time. Okay, here's number 4, which was an integration by parts. So that is an algebra and a trig right together. There's really no good u substitution. You could think of u to be the inside, but it's really a simple inside, that doesn't really help you with this x at all. So that's when, you're thinking, okay, maybe I need an integration by parts. So I got an algebra, I got a trig, so I do that. I'm going to kick out a 1/2 over here. Got my 8 here. Remember, we never divide that 8 over. Now when we're doing integration by parts, we don't. Okay, so I got u times v, so 8 times 1/2 is 4. Times x times sine minus v du. So I want to multiply these two together. I want to take v times du. That's why we can't have that 8 over there. V times du. 1/2 times 8 is 4. And then my sine, I do my antiderivative sine, got kicked out of 1/2 again. So it cuts that to a 2. It's negative cosine, so that turns to a plus. Okay, so there's my integration by parts example. I'm going to go back to the website and show you something their class asked about. They wanted some more integration by parts practice. So I'm going to show you that again. I showed you yesterday, but I'll show you again on the website. Okay, that's number 4. Number 5. Now, number 5 was an interesting one. Did anybody notice the blue that I did up here? The honors advance, I'm going to show this to my honors advanced math class today because they're doing identities. They're doing trig identities right now. What's 1 plus tangent squared? Secant squared. 1 plus tangent squared is secant squared. Secant squared over secant squared is 1. The antiderivative of 1 is x plus c. Stop right there. Okay? If you don't see it, then somebody in the other class said, well, why not let u be the bottom? 1 plus tangent squared. Well, here's the problem with that. How do you do the derivative of tangent squared? You got to remember that tangent squared really means this. How do you do the derivative of that? Bring down the 2 times tangent times what? the derivative inside, which would be secant squared. So the derivative of tangent squared is a real mess. 2 times tangent times secant squared. Now there is a secant squared setting there, but there's not a tangent setting there. So you can't, that's not going to work. What you're going to do is let u equal tangent. Why? Because I recognize that would make that 1 plus u squared, which is an arctan. So I see an arctan setting there. So I got a 1 plus tangent squared. Well, it's really 2 reasons I can do it. If I let u be the tangent, that makes this an arctan, 1 plus u squared. And what's the derivative of tangent? Secant squared. It's setting right there. So that's what makes that a good u substitution. So I do that u substitution. That takes care of that. It's a du. This is 1 plus u squared. The whole thing's an arctan u. And then so u is tangent. So arctangent of tangent, they're inverse functions. They cancel each other out. So arctangent of tangent just becomes x. Now, question usually comes up, what if you stop there? Well, again, probably not on the first time, because you should simplify something like that. Okay? So x, and know that that's x. But, you know, shortcut there if you recognize that identity. Maybe you didn't, and that's fine. You don't need to. You can still get it. Okay, here's number 6. Number 6 is one of those extra x situations. So you look at this and you think, okay, we could let u be the top. If we let u be the top, you get a 2x dx. Well, that doesn't work because then there's no x dx there. So the other option we have is let u be the bottom. Actually, that would have been our first thought before letting u be the top. We let u be the bottom, we get x minus 3. The du is just dx, so that takes care of the bottom. Now we got this extra x up here. Well, that's okay, because this is one of those where we can solve for x. We can let the x be the u plus 3. And then we put that back into there. So we get u plus 3 squared plus 1, which is fine. We can FOIL that out, do some algebra, and then we can split it up. Okay, so that's what we did early on, a few days back, with these extra x situations. So we let u be the bottom. We can solve for x. We can plug it in up there. U plus 3 squared is u squared plus 6u plus 9 plus the 1. So we get u squared plus 6u plus 10 all over u. Now we can split it. U squared over u is u. 6u over u is 6. 10 over u is just 10 over u. And that one we can do an ln on. So what do we got? We got 1 half u squared. Antiderivative of 6 is 6u. 10 ln u. And now we can put our x minus 3 back in. And we get that down. Okay, so haven't done one of those for a little while. I don't think there was one of those yesterday. Maybe there was. I don't remember. But the extra x, right? Let u be the bottom, kind of a scenario. Okay. All right. Number 7 is a pretty straightforward. And this is just a straight mark. I hope nobody was confused by that. That's just a straight mark in there. I don't know what that was. Let u be the bottom, 2 plus cosine. The du is negative sine x dx, which takes care of the top. Pull out the negative. We got 1 over u, that's an ln. Then you can do the red or the blue, whatever. Go back to x's, stay with u's, doesn't matter. Okay? And so now you just put that in there, negative ln2 plus ln3. You don't need the bars. Obviously, 2 is positive, 3 is positive. You don't need the bars. You just have parentheses there. Okay? And there's really no way to simplify those, so you just leave it alone. Okay? Well, I suppose you could put that together, couldn't you? Minus or whatever. I'm not going to make you do that, but this is ln3 minus ln2, which is the same actually as ln3 halves, right? That'd be one of those where on the AP test and the multiple choice they might do something like that to you, right? We got ln3 minus ln2. That's not. All right. Number 8. And then number 8 is a little bit like the one we had yesterday with the square root of x. We can let u be the inside, which is 5x to the 1/2. Nice thing about that is you get a 1/2 x to the negative 1/2, or 5 halves x to the negative 1/2. Now, where people really run into trouble in this one, though, is just that fraction, keeping track of that 5 and the 1/2 and everything. So you bring the 1/2 down, it's 5 halves x to the negative 1/2. I like to rewrite that x to the negative 1/2 as this, square root on the bottom, and that takes care of that. But this 5 halves is kind of in the way, so we move it over, and it's 2/5. So we got our 1 over square root of x dx. We take that out, and we can put in the 2/5 and the du. And then the rest that's left is the sine u. Okay, and then antiderivative of that, of course, is negative cosine, so, and then you put your 5 root x back in. All right, so that's how the 2/5 comes to be there, though, is your work here. So sometimes, so be careful. Be careful with that. Okay? All right, so the question came up in the other class, and I'll see if you guys have any questions about the website or about practice on integration by parts. Now, again, a couple integration by parts, maybe at the most. I don't want to see somebody doing U's and DV's on every problem. You can't do that, right? There's only probably a couple. More of them will be U substitution or just regular antiderivatives. But if you want to do a few more of those, because we don't have a lot of them in the book, problems, there's 2 places you can look. If you go to this, which is probably our better place to go, on most of these tests, there's at least one that's an integration by parts. Okay, the first one's usually a basic one or maybe a U substitution. This one's an integration by parts. Now this one's actually one you'd have to do twice. I told you we wouldn't have to do one twice. Here's one you can just split apart. 4 we said never do. 4 is not one we can ever do. 5 is another substitution one. This one is an integration by parts, so this one actually has a couple of integration by parts ones. This would be an arc tan like we talked about with that 16. Now I'm probably not going to make you do that. But that's what we talked about. And then this would be let U be the bottom. You could let U be the bottom and you'd be in good shape there. Okay? So most of these you can do, but not number 4. But there might be, that on every one of these sheets, I think there's always at least one that's an integration by parts. If you want to do one that you know is going to be an integration by parts, you can go to this website, and right here it says integration by parts. And what I told you was these 4 are integration by parts problems. Now, what I like about this is this kind of gives you the 4 different types I would probably give you. Here's an algebra with a trig, here's an algebra with an exponential, here's an algebra with a log, and here's just a regular inverse sum. You would just let U be the inverse sine, the dV would just be the dx. But really I would focus on these 3 problems. Okay, this one is one that you have to do twice. I said don't worry about it. This one is a really weird one, which we won't worry about either. Okay, this is what your integration by part ones are going to look like. Okay, something like this. Some algebra with a trig, algebra with an exponential, algebra with a log, something like that. Problem. Okay, so you could do those 3 or make up one of your own similar to that. Yeah.
Will we have like a integration by parts on like close to the board?
Like a definite integral. Remember, integration by parts that's a definite integral of a and b, you just do all the integration by parts all the way down to the end where you would normally put on the plus c and be done. When you get to there, you do the right bracket, put your numbers on, and then put them on. So it's just, you do everything all the way to the very end, and then you put your numbers on. Okay? Anything else? Anything else? Good. Yes.
If you give us a definite integral with a U substitution and you use the U numbers, do you need to have the actual one on there as well? Or do you just leave the answers?
No. So, like on the ones where I've been doing, I've been putting 2 of them there.
Yeah.
Yeah. You can have the red or you can have the blue. Either one. The answer's the same. Well, remember that, did I tell you that story about Myers Math class? Where he put 5 answers. I said there's an infinite number of answers if you just shift the graphs, and he put 5 of them, and 4 of them were wrong, and 1 was right, so he lost a bunch of points. Can't put wrong answers, so yeah, if you're going to put them both, make sure they're both right.
If they are both right, we get bonus points?
No. No, you just get it right. Okay, so practice. I'll be here early in the morning again if you want to come in and any last minute questions or anything. Okay? Yes.